So today I want to give some idea of a new design for shear force. So you had heard the shear force in your strength of materials. I was also repeatedly talking you that in a civil engineering structure, if there is load, if there is longitudinal member, if the load is acting along the y-axis, and member is horizontal, then the member will be subjected to bending moment and shear force, right? If the reinforcements are provided only on tension phase, then the design will be singly reinforced. And sometimes we had to require some reinforcement in compression zone also. Otherwise, the beam fails in completion. So under that situation, we told that the beam is doubly reinforced, right? So doing those things and reading many things, you will be able to make the structure resistive very good. But simultaneously, shear force is also coming. So all of you know, if a beam is simply supported, if the beam is and uh, simply supported, and if the member is subjected to uniformly distributed load, W, then bending moment is maximum bending moment, because in your structural analysis, you will be required to find out the internal forces developed at each and every section. At each and every section. So internal force developed, bending moment and shear force, and sometimes if it is a beam, the torsion may also come. Okay, for that, at each section of the beam, what is the internal stresses developed, you have to find out. That is the structural analysis part. Now, when we after structural analysis, we have to enter in on a structural design. So when we are going for structural design, we require the worst effect or worst affected location. So if a beam is simply supported, the maximum shear force is acting near the support. I think all you know the expression. If W is the intensity of the load acting throughout this span, L is the effective span, then maximum bending moment near the support is small WL divided by 2, and gradually it reduces to 0 at mid-span point. So maximum shear force is near the support, right? And from bending moment point of view, we got maximum bending moment is at the mid-span point, or somewhere near the mid-span point. And similarly, if the member is subjected to say some concentrated load at different locations, then we have to find out the bending moment at under the load. Out of that, those bending moment, which whatever is the maximum, that will be required for design purpose. Okay. So for designing with respect to bending moment, we had obtained some cross section, we had obtained some amount of steel required. Number one, if the member is singly reinforced, then it is only on tension zone, and if the member is double reinforced, the reinforcement is provided both in tension zone as well as compression zone. Okay. Now this beam, whether this beam is safe with respect to shear force or not, that we have to investigate. How we investigate? How we investigate? Okay. So that is the point. So similar to our bending moment at any cross section, and on that cross section at any location with respect to neutral axis. What is the neutral axis that we had obtained even in your strength of materials or applied mechanics, and we had also discussed at the very beginning, third or fourth class. Okay. Now shear. We had obtained at different location in the beam. Now at any location of the beam, we know what is the magnitude of shear force. What is the magnitude of shear force? Now the shear force is normally designated by the capital letter phi. Capital letter phi. Now this shear force X always parallel to the plane. Parallel to the cross-sectional plane. Parallel to the cross-sectional plane. That means this cross-sectional plane should be able to resist whatever the shear force will act or induce. Right? So first we'll have to say without any state whether it will be able to resist it or not. Now for this, there is slightly difference whatever we have done in our analysis. Now in our analysis, what we have obtained, the stress on any surface with respect to stress or shear is always parabolic in nature. If it is a rectangle, maximum stress is at neutral axis and minimum stress at external surface. So this you have studied it. So we have obtained that stress. Bending stress and shear stress, they are just opposite. In the section, the surface where the bending stress is maximum, their shear stress is 0. Shear stress is 0. Okay. Now, you so see one figure. See, this is a figure. This is a figure. Now, this is shear stress distribution diagram. This is idealized. This is not the actual shear stress diagram. Now, see here. These are obtained in our structural analysis or strength of materials Q. Shear stress at any location with respect to neutral axis. Is a P. P is the shear force at A is the cross-sectional area. Of the location, say here, upper part of this part is the A. And then Y. Y is centroidal distance of this area with respect to neutral axis. Okay. Then B. B is the width of the beam. Right. This note I will modify. Are you hearing me? Are you hearing me?
Yes, sir.
This note, whether it is visible for you or not.
Yes, sir.
Now this note I will modify. I will modify. After modify only, I will give you. Okay. At this moment, you just see. After modification, I will give you. You don't wait. Okay. So by this, we will be able to find it. Now this Q, whatever we had obtained, this is a theoretical part from analysis point of view. Because that is a homogeneous section, single material. But when we are coming for RCC, it is not homogeneous material. We convert it to homogeneous. It's two kinds of material which are having different characteristics. It is concrete and steel. See, in our last, we had got the complete stress. Hardly maximum 20, 25 in stress. But when we come from analysis to structural design, we'll modify our assumption. We'll modify our assumption. Now see here, I am showing, I am moving my mouse. I am moving my mouse. Had it been single cross sections B and D, our shear stress distribution diagram would have been, it is coming parabola this way, this way, this way, this way, and it will reach here. This is the shear stress distribution diagram. Right? But here, we had modified the shear stress distribution diagram in this way. Right? Now, shear stress distribution, see here, from the structural analysis of structure materials, we got Q maximum is equal to it is a P by BD is shear stress developed general expression, and the maximum is 3 by 2, that is 1.5 times 1.5 times P. Okay, but when we are coming for design, we will not utilize this. Point of view, it has no any validity. Okay, it has validity only with respect to structural analysis. Okay. Now see, the shear stress distribution of reinforced complete beam. So theoretically, the shear stress distribution in a rectangular reinforced concrete beam section depends on distribution of normal stress. Normally, the concrete in the portion below the neutral axis is assumed as crack. Hence, no tensile stress is resisted by this portion. The theoretical distribution of shear stress in elastic and limited method may be as shown figure A and B above, respectively. Figure A and B shown respectively. Now, I want to tell you, for the sake of simplicity, the value of a normal shear stress is taken as P by BD. Okay. So this is simple shear stress distribution. Are you looking my hand? My left hand? Hello?
Can't see, sir.
You can't see. How I will be able to show it?
Yes, sir.
Now you saw.
Yes,
Now you
sir.
saw. Huh? Yes.
Yes, sir.
Okay, very good. Now you can see.
Yes, sir.
Yes, sir.
Then you just give the concentration on my hand. So this is the cross-sectional surface of a beam. This is the beam, load is acting. So shear force is acting this way. This shear force is acting this way. That means this plane area has to resist this shear force. So this plane area, had it been a single material, then area is B multiplied by D. But according to, if we go for this expression, what is going to happen? This stress distribution here would have been, here it is 0, here it will be 0, and it will come this way. It will come this way. Maximum at neutral axis. But for the concrete is able to resist the tension. Now, because of this way, there is a possibility of tension. So on this part, no concrete is not allowed. There's a possibility of concrete. So that's why what is happened, what is done, we will take the average stress. We'll take the average stress. And this average stress will act throughout the area. This average stress will act throughout the area. So that will be considered. And this average stress will act uniformly at any depth. So that assumption is made, and here I have also written. So if that is the thing, then shear stress Q will be equal to just width B and depth D. Okay, had it been single material, then that D would have been capital D, overall depth. But it is an RCC. At the very beginning, when we had started single reinforcement, there we had made one assumption that concrete or yes, cover in tension zone is neglected. Cover in tension zone is neglected. So if that assumption we had assumed there, so it has to be applicable for any member, any construction. So that's why we will take small is effective depth. So we will be able to find out the shear stress developed or induced. Q is equal to P divided by BD. So see this, we had got this. So we had got this. Now see here, it is written P by BD and allows average shear stress on effective area and not on the maximum stress. So this is our basic assumption for design of shear in RCC. In steel, it will be something different. In steel, it will be something different. Okay, so that's why terms are given by the codes, code CODE of every country. Every country, in our India also, we are having code. I had repeatedly mentioned IS 456. It was revised in 2000. It is reprinted different times. So you can download this also. Did you do try to download this code? You downloaded this code? Yes or no?
Yes, sir.
So after download, did you had gone through it just like a novel? Not necessary to understand, not necessary to spend heavy attention. Just you go through it. I am asking all of you, just you go through 2 to 3 times without giving any strong attention. Just you go in, just like you are reading a newspaper. You will get many information. If you give some attention, then you will be able to digest everything. Okay, now here all this word, the use of concept of average shear stress tau average in the beam section of homogeneous material. See, homogeneous. So I think you are more clear compared to me what is homogeneous material. Means it will give same character in any direction. Okay, which is represented by tau average. Tau average, shear force divided by area of cross section is used. Okay, now we are coming with respect to code. What is the nominal shear stress for member with uniform depth? So this just I had reprinted the nominal shear stress for beams rectangular or flange section shall be obtained. This clause 40.1 IS 456/2000 is given by tau phi. Tau phi, see, we had written previously tau average, tau phi is equal to PU by BD. Hmm? P, because it is a limit state method. In case of bending moment, we have written mu. We have written mu. Use the suffix for factorization or ultimate. Hmm? So by this way, we will be able to find tau p. Right? Now this tau p, the nominal stresses. That nominal stresses, you do not misunderstand. Nominal means something minimum. No, we can say actually also the actual shear stress acting on the section. Very good. Oh. Sashi. Moi, আজি মই লিখিম বস্তুটো। মই আজি লিখি মানে গধূলি পঠাই দিম পাই যাবা। এইটো অন্য কথাটো নাই। তাৰমানে আজি মই কথা নাই। The actual stress, although the word nominal is there, it is the actual shear stress. Now, second depth. Sometimes we may construct the RCC beam fairing depth for requirements. That means tapering. You not necessary to worry. You not necessary worry because the IS-453 always should be with you in your practice. Okay. Then problem is coming. This tau phi, whether for rectangular section or for tapering section, will get some value. In our beam, the beam may be without reinforcement, the beam may be with reinforcement. Okay, the beam may be, no, it cannot be. If it is a flexural member without reinforcement, it will not be possible to restrain it. So it is a reinforcement. Now this shear force tau p, whatever acting, it has to be resisted by the cross section, the concrete and steel. Concrete and steel. Now for this, there are some relations. Now, what is done in our when we had design with respect to bending moment, we had used tension reinforcement. Now again, it is going this way. So when it is going away, these reinforcements are this way. Reinforcements are this way. So this reinforcement will also be able to resist this force. That means together with this, section and this reinforcement will be able to resist this. Now, how much this cross section together with steel will be able to resist? That we'll have to find out. So that to find out that, IS-456 gives some idea. IS-456 gives some idea. Now, design strength of concrete. Design strength of concrete clause 40.2 point is the design stress tau C. See, previous one was tau V. Now this is C. This C means the design strength of the concrete together with bending steel. So for that, what we'll have to find out? We have to find out what is the percentage of steel we have provided. Percentage of steel we have provided. So AST we have provided, that we have provided in here. They are, say, try to remember, say 4 numbers, 16 tall. number 20 Thor we have provided. So 4 number 16 Thor means 800 millimeter square. 800 millimeter square. So if the cross section of the beam, effective cross section of the beam is 200 by say 350, then percentage of steel will be equal to 800 multiplied by 100 divided by 200 multiplied by 350. So this we will get, percentage of steel we will get. Now, in IS 456, there is a table number 19. So in table number 19, you will get what is the capability of the shear resistance with respect to percentage of steel. With respect to percentage of steel. So that in that table, you will get the first column. The first column will represent the percentage of steel. Then second column represent shear resisting capacity with respect to M15 concrete. Next column represent shear reinforcement capable to resist M20 concrete. Third column represents by M25 and so on. So with respect to first column, by finding this PT, tensile steel. Now if V, so, no, this time is tau C. Compare tau V and tau C. Your tau V may be less than tau C. Your tau V may be equal to tau C. Your tau V may be greater than tau C. Tau V is the stress induced. Tau C is stress that can be resisted. So if tau V is less than tau C, that means induced shear stress is less than shear that can be resisted. So under this situation, the member is safe. The member is safe. No problem. That means we do not require any additional reinforcement. We do not require additional reinforcement. Now, if tau V is equal to tau C, it is a critical. We may provide, we may not provide. But if tau V happens to be greater than tau C, that means induced on the member is more than the shear that can be resisted by the section. So the member will not be able to, the member will fail. So under that situation, what will do? Now again, a condition is given. Tau V greater than tau C. How much? Up to how much we can go. So for this, again, this table is given. Again from this. So for object of this lab, this is the particle factor. Okay. Now, okay. So this is not much requirement now. Let's see here. This table, tau C maximum. Now tau C, that means tau C, tau V. If tau V happens to be more than these values, the member will not be able to resist. Okay. Now what is happening? That means if tau V happens to be greater than tau C, but less than this value, we can come to conclusion that we shear reinforcement, and without any changing dimension or without any changing amount of steel, we will be able to design it. But if tau V happens to be the time that tau C maximum. Under that situation, the problem arises. Just by use of shear reinforcement, the beam will not be able to make resistive. So under that situation, we will be required to sense something. We may have to require sense the cross section. We may have to sense the amount of steel. That means we may have to enlarge the section. We may have to increase the amount of steel. Those things will be required. Okay, those things will work. So here I am writing. See, the yielding of the shear reinforcement at ultimate limit state is essential to ensure a ductile failure. However, such a failure will not occur if the shear reinforcement provided is excessive. If the total cross-sectional area A as B is A as B, shear area of shear reinforcement of stirrup legs and bent up bars exceeds a certain limit, it is likely the section becomes strong in diagonal tension compared to diagonal compression. Hence, the shear compression failure may occur even before the shear reinforcement had yielded. Such a central situation is undesirable. Compression failure is very much dangerous in case of persistent member because it will not give any indication. If the member is getting tension, it will give indication. Compression failure means it is brittle failure. It is a brittle failure. Brittle failure is a failure which is occurring without giving any indication. So under that situation, it is said that if A as a B, the legs, stub legs, and bent up bars exceeds the certain limit, there is a possibility of increase of compressive stage than the tensile stage. So that's why the design in order to prevent such a shear compression failure and to ensure yielding the shear reinforcement at ultimate limit considered limit of resistance VUS by limiting this value. That means this is an expression. Okay, this. Now, if the calculated nominal stress tau V at a beam section exceeds the limit tau C maximum, the design should suitably be reversed. So this I told you already. Okay. Now, something I will just talk today. Now, how to design it? So, very simple. You will get in IS 46 whatever I am now quoting. Now, VU is known to us. So, we will find out tau V. VU divided by B into T. Then, with respect to area of steel, we will try to find out the tau C. Now, we will compare the tau V and tau C. If tau C is within the limit of maximum permissible value, then our conclusion is that only shear reinforcement will be sufficient. Only shear reinforcement will be sufficient. Okay. Now, how shear reinforcement will be there? How shear reinforcement will be there? The shear reinforcement, there are number one, link, stirrups. It is a link. Secondly, bent up bars. That means bar reinforcement we have provided with respect to bending moment. From bending moment point of view, all the reinforcement we do not require near the support. So to resist this shear, we can raise up the reinforcement whatever available at the bottom to upper surface. This will be able to resist the shear. So these are called bent up bars. Number of link, the reinforcement whatever longitudinal we have provided, those will be tied up with the help of ring. These are the things so by this. Okay, and sometimes both both link and bent portion. Okay. Now, how much? How much? So what is happening? The PU is the factored shear force. Tau C, Tau C is the shear that can be resisted by the cross section together with amount of steel. Okay, so we can find out PC. We can find out VC, capital VC. So capital VC will be equal to tau C multiplied by cross section area, small b into d. Okay, then which is still not resistance. So PUR, unbalanced pressing. So this is equal to PU minus VC. Minus VC. Okay. So this PU or for this PUR will be required some reinforcement or stirrups. So that how we will be able to find out. This expression is also given in your IS 46. Just that is the base. It is there's somewhere I had written capital A as a B. So that for the time we replace A as a B, small a as B. So here we will be required what is will be required to find out the spacing of the stirrups and diameter of the stirrups. Two unknown. Out of these two unknown, one will assume. The stirrup, the spacing we cannot. The spacing we cannot assume. So we can assume diameter. Now for stirrup, for our normal construction, say for building, it has some specification also. It may range from 5 millimeter to 12 millimeter diameter. Okay, it has some specification in IS 46. If you have already downloaded, you can go through it. That will be useful in your code, in your examination. So for that, we'll be able to find out spacing. So spacing will be equal to small a as a b multiplied by small a as a b multiplied by d. D is the multiplied by point spacing is equal to 0.87 Fy A as a B multiplied by D divided by PUR. Now here 0.87 Fy, you know, small ASB or capital ASB, cross-sectional area of stirrup. D is the effective depth of the beam, and VUR is the unbalanced shear force. When we go for solution of the problem, we'll be able to see. Very simple. Now this A as a B is dependent on there is no. I think it will not be possible to imagine it. It will not be possible to imagine. A as a B, when we are going for vertical legs, those will be called as two leg, single leg, two leg, three leg, four leg, and so on. So this A as a B is equal to A as B is equal to n times small a as b, where n is the number of legs and small a as b is area of cross section of the diameter of stirrup. So from this we will be able to find out spacing required. Diameter we have already considered. From this we'll be able to find out the spacing required. So for that also there are some specifications. These specifications are given in the code. This specification cannot be more than 0.75 times effective depth. Okay. So to conclude here today,